Okay, I had to stop that previous video. I kind of got lost in what I was doing, and I had to reread the question. They actually want you to map from this rectangle in the UV plane to the XY plane. Okay, and I got stuck because I was trying to do something different here. We already have the rectangle in the UV plane. It's U equals 1, U equals -1, so obviously it's not to scale over there. V equals 1 and V equals 3. That is the rectangle, okay? And we're just figuring out how did we map it onto that XY plane, okay? So where I left off was correct. We just want to solve these, so like X is some function of U and V, and Y is another function of U and V that would map it onto that XY plane. And I got confused for a second because that's typically not what we want to do. We want to take something like what's in the XY plane and make it easier in the UV plane, okay? But it's okay. We got it. We'll get this figured out. So again, you're going to set them equal to each other. So 2x plus U equals V minus X. So 3x plus U is V. And then 3x would be V minus U. So x is 1/3 V minus U. Okay, that will be our x transformation. All right, and then our y transformation, we can just sub that into either of them actually, and you would get the same answer. We tend to like this one maybe. So y is 2 times 1/3 V minus U plus U. So that would be 2/3 V plus 1/3 U. Or we could write it as 2V plus U over 3. Okay, and there we have it. Okay, whew, here we go. We're going to do another one like that. Okay, this one's a little trickier. Let's see. Now we have R is bounded by, by the hyperbolas y equals 1 over x, y equals 4 over x, and lines y equals x and y equals 4x in the first quadrant. Okay, find the transformation that maps T, which is a rectangular S in the UV plane, onto R. Okay, so again, we're in the UV plane, some sort of rectangle S, but we'll map it onto this in the XY plane. Okay, so again, y equals 1 over x. This is going to get a little messy, right? Y equals 1 over x would look like this. Okay, y equals 4 over x is going to be at every point 4 times higher than that, right? Okay, so not the best drawing there, but this would be y equals 1 over x. This would be y equals 4 over x. And then we're going to have y equals x. And we're going to have y equals 4x. Okay, so we're talking about this region R right here. Okay, so we're same thing. We're going to look at the two that are similar to each other. So we have y equals 1 over x and y equals 4 over x. Well, let's just change that to y equals u over x, where u is between 1 and 4. Okay, and then we also have y equals 4x and y equals 1x. So let's just change that to y equals vx, where v is between 1 and 4. Okay, so again, that's what we have, and we can just set them equal to each other. So u over x is vx. Okay, so x squared would be u over v. So x will be the square root of u over v. And only positive because that's where our region is, right? Y then is vx. that'd be v times the square root of u over v. Okay, so let's simplify this a little bit. If we put v squared u over v, right, then we'd have the square root of uv. Okay, so y is the square root of uv. So there's your transformation. It would take that nice rectangle and map it onto that weird shape. Okay? All right, we are getting close to the point where we want to do some integrals then, right? We definitely are excited to do some integrals. So we need to get into just a little bit of a trick to doing integrals, okay? Obviously, you're going to switch to your other coordinate system and integrate with respect to like u and v instead of x and y, but we do have a little special thing that has to go along with it, okay? And I think your book gets really into it, and I'm going to try to kind of make it really basic terms so you understand where we're coming from here, okay? Let me find my notes here. Okay, so again, we're taking this rectangle that would be in the UV plane, okay? Some point here might be U naught, V naught, okay? And then we go distance delta U, and this would be U naught plus delta U, V naught, okay? And then we'd have delta V, and this would be U naught, V naught plus delta V. And up here, U naught plus delta U, V naught plus delta V. Okay, the area there then would just be delta U, delta V. Or we know when we're integrating, then you'd have a du, dv. Okay, well, now we have to think about that being kind of a mangled mess in the xy plane. Where, maybe it looks something more like this. Okay, and maybe x naught, y naught is here. Okay, so now let's say that this delta u side maps onto this side here. Okay, well, then what we can do is we can use a vector to describe that side. Okay, we would take that delta u, and now what we need from it is in the x direction dx du, okay, where again x is some function of u and v, okay, and y again is some function of u and v also, okay. So we would have to take that delta u and then get it going in the right direction, dx du in the I direction, okay, and dy du in the j direction. Okay, get your kind of your horizontal and vertical components from what was u, get them into their x and y components. Okay, so then this other side here, I'll use a different color. It's blue. This side might correspond to this side here. Okay, so we got to take that delta v that was in the UV plane and figure out how that v, right? Because u is constant there. Okay, but we're going to get that v transformation. So we'd have dx dv in the I, and then dy dv in the j. Okay, that's the basic idea there. Okay, and again, those would be vector functions that are going to get you those sides. Okay, in really basic terms. Your book, I think, takes like a couple pages to prove it in some different ways. I think that this is all that you really need. Okay, so the only thing that we need to add to that then is to find that area. When you have a vector, you do the cross product, right? If you do the cross product of two vectors, you get the area of the parallelogram that it creates. So our area would be delta u dx du in the I, dy du in the j, crossed with delta v dx dv, dy dy dv. Okay, so we're going to do that cross product. All right. So we'll do that kind of quick here. First of all, delta u and delta v are constants, so we can take them out. And then we're going to do the cross product of what's left. So dx du, dy du, dx dv, dy dv. Okay. Now that just that cross product part here. Okay, so it's like your determinant, right? So we're going to have dx du, dy dv minus dx dv dy du. That is called the Jacobian of the transformation t. Okay, I'm going to get to that in a second, but we're going to have that times your du dv. Okay, so that's the piece that you have to add into your integral, right? We're going to switch our we're going to switch and use du dv. We also have to use the Jacobian there. Okay, so the Jacobian of the transformation t given by x is some function of u and v, y is some function of u and v also, okay, is written like this, okay, which is the determinant it's dx du dy dv minus dx dv, I'm sorry, dy dv, no, dy du. No, I got it. I just did the dx dv first and then dy du. Okay, that's called the Jacobian. And you have to include the Jacobian when you do your integral. So if we're switching from delta A is dx dy, it's going to equal, oops, and I should put the, forgot the bars on the side there. It's the Jacobian. Du dv. Okay, so again, if we have an integral over r in your xy plane, then we can do it over s in the uv plane, okay, where we're going to swap out those x's for u's and v's. We're going to swap out those y's for u and v's. Jacobian. Du dv. Okay, and that's the point where I try to remind you it's going to make more sense once you see an example. Okay, one quick example is you've seen this in polar. Okay, in polar, we take our x and make it a function of r and theta. It's r cosine theta. Okay, it's just like u and v, right? I could just as easily do u cosine v. Okay, and then y is another function of r and theta. That's r sine theta. Okay, now here's the fun thing. Your Jacobian of r and theta. Okay, we're going to do dx dr, dx d theta, dy dr, dy d theta. And again, we were just using, instead of u and v, r and theta. It's the same thing. Okay, so dx dr is cosine theta. Dx d theta would be negative r sine theta. Dy dr is sine theta. Dy d theta would be r cosine theta. Okay, so this is going to be r cosine squared theta minus negative r sine squared theta. Okay, so that's plus. So that's just r dr d theta. There's that extra r that we always put into our polar integrals. Okay, so when we do that integral over r of a function in x and y, dx dy, right, we switch it to a function of r cosine theta and r sine theta, r dr d theta. Okay, so you've seen that before. We've used the Jacobian before without even realizing it. Okay, all right, I think we're ready for an example. Let's take a look here. Okay, the first one, the first one has us do an integral. Okay, your first one here, they actually tell you how to transform it. I actually think it's easier if they don't, because then you can just kind of figure it out yourself. But we're going to use the ones they gave you, just so that you see it. Some kids do like to be given that because they just want to be sure that they're doing it right. This is number 16 in your book, if you're following along. We're going to do the integral over r of 4x plus 8y dA, where r is a parallelogram with vertices negative 1, 3, 1, negative 3, 3, negative 1, and 1, 5. Okay, and we're going to use the transformation x is 1/4 u plus v, and y is 1/4 v minus 3u. Okay, so first of all, let's just see why we don't want to have to do that. If we graph this out, okay, we would have negative 1, 3, 1, negative 3, 3, negative 1, and 1, 5. Okay. Not super to scale, but we can see this would be y equals negative 3x plus 8. And you could just figure this out by using the 2 points. Okay, so I already took the time to do it for you. The sides are linear, so. Okay, so you can see why we wouldn't want to do that. Okay, if we had to integrate with respect to x and with respect to y, we'd have to split it midway. Okay, actually, we might even have to do it a couple times. But that's not an easy area to integrate. Okay, we'd have to do x goes from, let's see here, 0. Let's see, x would have to go from, well, here. If the top function, does it switch exactly? 1, 5? Yeah, one. I guess we would only have to do two integrals. but let me get a dashed line in there. Okay, so we'd have to do one integral from x is -1 to +1 with x plus 4 and -3x for the y's. Then we have to switch and go from 1 to 3 with -3x plus 8 on the top for the y's and x minus 4 as they bottom up for the y's. So we'd have to do that double integral, okay? I'm sorry, we'd have to do the double integral broken into 2, okay? We wouldn't want to do that, okay? Like again, we'd have to do -1 to 1, x plus 4, -3x, 4x plus 8y, dy dx, plus your integral from 1 to 3, x minus 4 on the bottom, 3x plus 8 on the top, 4x plus 8y, dy dx. It's not awful, right? But we're going to see how the transformation would help us. So first of all, they tell us these are the transformations that we're going to use, okay? So all we're going to have to do is sub them in. So that 4x, so we can do that right away. 4x plus 8y will equal 4 times 1/4 u plus v plus 8 times 1/4 v minus 3u. Okay, so that's going to give us u plus v plus 2v minus 6u. Okay, so that'll be 3v minus 5u. Okay, so that will be the new thing that we're going to integrate. And then, excuse me, we will do our Jacobian. Okay, so we'll do the dx du, dx dv, dy du, dy dv. Okay, so dx du would be 1/4. Dx dv would also be 1/4. Dy du would be -3/4. And dy dv would be 1/4. Okay, so we've got 1/16. Okay, because that's, oops, we're getting glitchy here. I'm going to have to start a new video. 1/16 minus -3/16. So we'll have 4/16 or 1/4. Okay. Here we go. So almost there. We're going to have our integral of 3v minus 5u times 1/4. And then we have a dv du. Okay, so the last thing we need to do is figure out our bounds, what u and v are between. Okay, and we can just use the 4 equations that we got, okay, when we drew this out. So if we were along, let me get a different color here, I'm getting sick of purple. Okay, so if we were along the line y equals x plus 4, okay, well, x is 1/4 u plus v, and then y is 1/4 v minus 3u. Okay, when we expand that out, we'll get, it looks messy, but we're going to have 1/4 v minus 3/4 u equals 1/4 u plus 1/4 v plus 4. The 1/4 v's cancel out, and we have negative u equals 4. So u is -4. Okay, and we should expect that because we knew that it was supposed to be a rectangle. So it's just, these are all going to work out to just be a constant like that. Okay, so then if we're along the line y equals x minus 4, we will have y is 1/4 v minus 3u. And again, 1/4 u plus v minus 4. Okay, so if we go through that same thing, what we're going to be left with is negative u is negative 4. So u is 4. Okay, so u will be between negative 4 and 4. Okay, and then the other side is going to get us our v's. Okay, so y equals negative 3x plus 8. We'll have 1/4 v minus 3u equals negative 3/4 u plus v plus 8. Okay, so 1/4 v minus 3/4 u equals negative 3/4 u minus 3/4 v plus 8. And again, we got the negative 3/4 u that cancel out. Add the 3/4 v to the other side. V equals 8. Okay, and if we did the same thing with y equals negative 3x, we're going to end up with v equals a 0 over there. Okay, so v will go between 0 and 8. All right, and there you go. Okay, so now you would just do this integral here. Okay, I will leave that for you to do, but know that for the answer, you should get 192. Okay, all right, let's take a look at another one. And the next one is one that they have you come up with it on your own. Okay. Section number 23 in your book. So we want to do the integral over r of x minus 2y over 3x minus y dA. This one's a little bit different because they don't tell you what transformation to use, and I think it's easier. Okay, so they just tell you that r is the parallelogram enclosed by x minus 2y equals 0, x minus 2y equals 4, 3x minus y equals 1, and 3x minus y equals 8. Okay, so what I would do, and you should too probably, is I would say, all right, then x minus 2y is u, and u is between 0 and 4. Okay, and 3x minus y is v, and v is between 1 and 8. Okay, then that also helps because look at your substitution, what you're going to do there. Okay, but anyways, we'll get there. Then your Jacobian. Let's see here. We do need to get y in terms of u and v and x in terms of u and v. So we do have to have y is some function. Oops, usually they use h for the y. Okay. But here, let me show you something else over here. I'll keep going with this one. Sorry, lost my train of thought. Y is some function of u and v, and x is some function of u and v before we can do our Jacobian, right? Okay, so what we have here, we can do some subbing in, whatever we want to do here. So we have x minus 2y is u, and 3x minus y is v. Okay, so with this one, we can say x is u plus 2y. Okay, and then we can sub it into this one. So 3 times u plus 2y minus v, minus y equals v. Okay, I'm just checking my work so I don't get too far ahead of myself here, because I tend to do that. Okay, so 3u plus 6y minus y is v. So then we have 5y would be v minus 3u. So y will be 1/5 v minus 3u. Okay, so we've got our y. Y is 1/5 v minus 3u. Okay, so now we just need our x. So we can plug that. Now that we have y, we can plug it into either equation for y. So we might do x minus 2 times y okay, equals u. Getting stuck here on my Chromebook. Okay, so x will equal u plus 2/5 v minus 3u. Okay, so we've got u plus 2/5 v minus 6/5 v, or u, I'm sorry. So x is negative 1/5 u plus 2/5 v. Okay, so we could factor out a 1/5, and we can be left with 2v minus u. Okay, so x is 1/5 2v minus u. There we go. Okay, good so far? All right, now when I wrote the problem, this y didn't go in there, and that's an important one. Okay, all right, we're almost done. So now all we need to do is get our Jacobi in there. Okay, so remember we need to do dx du. Oops, I just wrote y. Come on, this Chromebook is killing me. Okay. Dx du, dx dv, dy du, dy dv. Okay, so dx du would be negative 1/5. Oh boy, negative 1/5. Okay, dx dv would be 2/5. Dy du would be negative 3/5. And then dy dv would be 1/5. Come on, Chromebook. Let's go. Okay, so then we would have negative 1/25 minus a negative 6/25. So we'd have 5/25, which is 1/5. Okay. All right, we are almost ready to roll here. Okay, so now here's the super nice thing. Okay, in our integral that x minus 2y over 3x minus y, that's just u over v. Okay, so they made that really nice for us. So we're doing the integral of u over v And then we have the 1/5 from the Jacobian, which I'm going to put out front since it's a constant. Okay, and then our du dv. And u is between 0 and 4 because that's what made it way at the beginning. And v is between 1 and 8. Okay. And again, I will leave that integrating to you because I know you can do it. You should get 8/5 the natural log of 8. It's a really straightforward integral there. And it's even separable if you want to do it that way. Okay. This Chromebook is freezing up on me, so I'm going to stop the video here and probably hold off on any too advanced examples here. We'll see. Okay.